Today we're going to work on two equations, Charles' law and Gay-Lussac's law, both of which include a new variable, which is temperature. So yesterday you mainly focused on volume and pressure. Again, volume is the amount of space something takes up. Pressure is created by the collision of the gas molecules themselves with the wall of the container that they are within. And so we found that as volume gets smaller, pressure is going to increase and vice versa. So as your volume gets larger, pressure decreases. So today we're going to look at the relationship between volume and temperature and pressure and temperature. The first thing before we can start with the equations is that you have to understand that we have kind of three temperature scales. We're used to using Fahrenheit in our everyday life. When we did specific heat earlier this year, we worked with degrees Celsius. Now we're going to work with the Kelvin scale. So if we'd been in class, we would have spent more time with this, but the Kelvin scale is based on a temperature scale in which there are no negative temperatures. The lowest possible temperature is absolute zero, which is 0 degrees Kelvin. So in these equations, we must use Kelvin because those negative temperatures impacts how the problem solves out. And so again, this helps eliminate some of those issues created by negative temperatures. So you have a formula that to take something to Kelvin, and notice that it isn't degrees Celsius like degrees Celsius or degrees Fahrenheit, but it's just Kelvin, uppercase K. And so what you do is you take your temperature in Celsius and add 273. So for example, we want to change an example A, Kelvin to Celsius, so we would use that Kelvin is your temperature plus 273. Your temperature is 32 degrees Celsius, so you just substitute that in, add 273, and just pretty simple forward that you add it together and you get 305 Kelvin. In example B, sometimes problems want you to go back to Celsius because Kelvin is a hard temperature scale to understand to begin with, and so Celsius, and then you could even work towards Fahrenheit, is a little bit easier yet. So in our original equation, we have that Kelvin is equal to degrees Celsius plus 273. So if you wanted to get degrees Celsius by itself, you would need to move that 273. So because we're using addition, we would then subtract. So in order to rearrange that, so if you wanted to go degrees Celsius from Kelvin, you take your Kelvin temperature minus 273. So in this problem, you're given a temperature of 275. So you subtract the 273. So you have a positive 2 degrees Celsius. So again, temperatures must always be in Kelvin using that addition of 273. So where we're going to use that is to start out, Charles' law looks at the relationship between volume and temperature. So if you think about it in terms of a balloon, and if you have this, you could try it. If you inflate a balloon and tie it off and go stick it in your freezer, you're going to find a balloon that's shriveled up kind of like a raisin. If you allow it to sit out, that balloon is going to return to its original volume. So if one goes up, the other goes up. So as temperature increases, volume increases. And that's because the gas molecules, temperature is a measurement of the kinetic energy of the particles. So those gas molecules are moving faster and faster, and so they are going to have more space between them, which allows them to expand. Again, a unique property of a gas. So vice versa, if volume decreases, the temperature is going to have to decrease as well. So we have a volume temperature equation where we have V1 divided by T1 is equal to V2 over T2. So much like yesterday, the 1s represent the initial or starting conditions, the 2s represent the ending conditions. So the thing is, because it's a direct relationship, we have it set up where we're going to have to cross multiply to solve. So in this first example, it says that a sample of argon gas has a volume of 5.4 liters. So that's my V1. And it's at a temperature of 15 degrees Celsius. So that's my T1, that pairs up with it. The thing I like to do right away is go ahead and put that into Kelvin so I don't forget. So add my 273. So 15 plus 273 gives me 288 Kelvin. And then it says what is the volume of the gas after the temperature has been increased to 42 degrees Celsius. So we know that our second volume is what we are solving for, and the new temperature is that 42. Again, we have to swap that over to Kelvin by adding 273, and so you get an answer of 315 Kelvin. Okay. So in our equation, we have that V1 over T1 is equal to V2 over T2. So I can go ahead and start substituting in. So my initial volume was that 5.40 liters. And that initial temperature, again, we're using the Kelvin, is 288. Is equal to, we do not know my new volume, so that's X. And then new temperature is 315 Kelvin. So what you can do to solve this, because we have a fraction, is I like to use cross multiply and divide. So what that means is you maybe have seen something like this in your math class. So you multiply what's diagonal to one another, and I'm going to rewrite that out. So what's diagonal to 5.4 liters is 315 Kelvin. So I can rewrite that as 5.40 liters times the 315 Kelvin is equal to, and the X is diagonal to the 288. So we have X times 288 Kelvin. This then gets that fraction part gone. There's more than one way to solve this, but I find that cross multiply and then divide is the easiest method. This looks a lot like Boyle's equation then, so then all we need to do is get X by itself, and division is what's going to take care of that. Those cancel on the right, Kelvin cancels on the left. So mathematically what you need to do to find your X is take 5.4 liters times 315 Kelvin, hit enter on your calculator, divide that out by 288, and we get an answer of 5.91 liters. And so we can see that the temperature increased, and therefore volume increased. This next one works with pressure and temperature, so it's very similar, but the only substitution is we have P instead of T. Direct relationship again, so if one goes up, the other goes up. So in the wintertime, oftentimes you have to add air to your tires because the pressure decreases because temperature has decreased. In the summertime, you may have to let pressure out because of a temperature rise. So we have this container reach a temperature of 55 degrees Celsius and a pressure of 965 torr. So we could go ahead and take our first temperature of 55 degrees Celsius. Like the last one, you want to change to Kelvin right away, so that way it's one less thing to keep track of. So when we add those together, I got 328 Kelvin. And then we are working with pressure, so my P1 is that 965 torr. And we have a T2 and P2. Continuing to read the problem, it asks what's the temperature in Celsius. So I'm solving for temperature in here. So that means I should have my new pressure, and that's 850 torr. So we have that our formula is P1 over T1 equals P2 over T2. So then you can start substituting in what we identified. So the 965 torr over the 328 Kelvin is equal to our new pressure of 850 torr, so we can see that pressure is dropping, so we could probably safely assume that temperature is dropping. Again, you cross multiply, so you multiply what's diagonal to one another. So that means we're going to take 965 torr times X equals 328 Kelvin times 850 torr. Now, it does not matter which side these two end up, so these could have had the 965 and the X on the right-hand side, and the 328 and 850 on the left-hand side. Again, the math is the same, you're just moving something away from X. So we divide just like what we've seen to eliminate. So again, in order to get x, we need to multiply and then divide. I can see that my TOR have eliminated, so my x is equal to 288.91, it looks like, Kelvin. It specifically asked in the problem to put it in Celsius, so just subtract 273, and when you do that, you get an answer of 15.91 degrees Celsius. So the last two examples, real quick, are just working on figuring out which one to use. So in example A, I can see that it has temperature and volume because I have Celsius and liters. So you just have to look at what your units are to decide which of these two you need. So I know that my T1 is 40 degrees Celsius. Add 273 to it, you get 313. My V1 is going to be that 2.30 liters. My T2 says to what temperature in Celsius, so that's what I'm solving for. And my V2 then, my new volume, is 6.50 liters. So that means I'm using the V1, T1 equals V2, T2 equation. And then for our second equation, if you look through, and I'm going to scroll down here in a moment, we have temperature and pressure. So this equation is going to be the P1 T1 equals P2 T2. Again, your units and how the problem is worded will help decide that. So go ahead and take a second to pause this video. I'm going to work out the rest of the problems and you can check out how you did. So I went ahead and finished posting the answers for this. So for example A, I got an answer of 884.57 Kelvin by subtracting the 273. That drops it down to 611.57 degrees Celsius approximately. And then the last one is working with the P1 T1 equation. And so when I multiplied and solved it out, I got an answer of 2.31 millimeters of mercury. So that's what your homework will be based on today. Let me know if you're struggling or if you have any questions.